Welcome to this explainer. Today, we're going to completely demystify electrochemistry. We're starting way down at the microscopic level with these invisible electron transfers, and we'll build our understanding all the way up to the commercial batteries that are literally powering your world right now. So let's jump right in. Here is our roadmap for today. We'll start by reviewing redox chemistry, then move into the anatomy of galvanic cells, calculating cell potentials, predicting redox spontaneity, and finally, we'll wrap up with batteries and fuel cells.
Section 1. Reviewing redox chemistry, the fundamentals of electron transfer.
To understand electrochemistry, you really have to think of electrons almost like a physical currency. A redox, or reduction-oxidation reaction, it's simply an exchange of that currency. Now, an element's oxidation number helps us track its electronic environment. When an atom undergoes oxidation, it's essentially spending or losing electrons, so its oxidation number goes up. Conversely, reduction is earning or gaining those electrons, meaning its oxidation number drops.
The thing is, when you're looking at complex aqueous redox reactions, keeping track of that currency exchange gets, well, pretty tricky. And that's exactly why we rely on the half-reaction method. It's this incredibly structured approach where we literally split the oxidation and reduction processes into two separate skeletal equations. By balancing our elements, using water for oxygen, protons for hydrogen, and finally electrons for the charge, we make absolutely sure we never lose a single electron before merging it all back into one perfectly balanced equation.
Section 2. Anatomy of galvanic cells, harnessing the power.
Check this out. If you drop a simple copper wire into a clear aqueous silver nitrate solution, you trigger a spontaneous transfer of electrons straight from the copper to the silver ions. The result is wild. The copper wire dissolves right into these blue copper ions, and gray, fluffy elemental silver just sprouts right onto the wire. It's a beautiful chemical change, for sure. But because that electron transfer is direct, all that energy is completely lost to the surrounding environment as heat.
So, the big question: how do we actually capture that lost energy? Simple. We separate those exact same reactants into two different beakers, or half cells. This is your classic galvanic or voltaic cell. By preventing direct physical contact, we literally force the electrons to travel from the copper to the silver through an external wire. And guess what? That flowing stream of electrons through an external circuit, that is electricity. We've just created usable power.
For this to make sense, knowing your electrodes is absolutely crucial. The anode is where oxidation happens. It's where our electron currency is spent and pushed out into the wire. The cathode is where reduction occurs, so it's the receiver of those electrons. But wait, for this continuous flow to work, we need an unsung hero, the salt bridge. The salt bridge lets inert ions flow back and forth between the half cells to maintain perfect charge balance. Without it, the whole reaction would just instantly grind to a halt.
Now, scientists love a good shortcut, right? Instead of drawing out those complex beakers every single time, we use this really elegant shorthand called cell notation. You always read it left to right, anode to cathode. Those single vertical lines, they just represent physical phase boundaries, like between solid copper and aqueous copper nitrate. And that double vertical line in the middle, that's our salt bridge connecting the two halves. It's a super quick way to understand exactly how a cell is built. Section 3. Calculating cell potentials, measuring the push.
Okay, this brings up a really fascinating problem. Potential, or voltage, measures the driving force pushing those electrons. But here's the catch. You can't measure a single half cell in isolation. An electron transfer fundamentally requires both a donor and a recipient. So if we can only ever measure the difference between two half cells, we urgently needed a universal baseline to compare everything against.
Enter the standard hydrogen electrode, or the SHE. The scientific community got together and universally agreed to make this specific half cell our absolute zero-point reference. It's designated as having a standard potential of exactly 0 volts. It's basically an inert platinum electrode sitting in exactly 1 molar aqueous hydrogen ions, with hydrogen gas bubbling over it at exactly 1 bar of pressure.
See how we use that 0-volt baseline in practice? If we want to find out the standard potential of a copper half cell, we just hook it up to the SHE. Because the SHE is strictly defined as 0, whatever number pops up on the voltmeter, like this positive 0.337 volts here, is 100% attributed to the copper half cell. And boom, that value becomes copper's standard reduction potential.
Thanks to the SHE acting as our baseline, chemists have been able to map out standard reduction potentials for pretty much every known half reaction. And with those reference tables, we can calculate the standard cell potential for literally any theoretical galvanic cell. All you do is take the standard potential of your chosen cathode and subtract the standard potential of your chosen anode. It's really that straightforward.
Section 4. Predicting redox spontaneity. Will it work? Calculating that voltage isn't just some abstract math exercise. It tells us instantly if a reaction will actually happen on its own. A positive cell potential? That means the reaction is spontaneous. The electrons want to flow, and your device powers right up. But if you crunch the numbers and get a negative potential, that's non-spontaneous. The reactants won't naturally exchange electrons in that direction unless you physically force them to by pumping in outside energy.
Section 5. Batteries and fuel cells. Electrochemistry in the real world.
All right, let's take all of this into the real world. Commercial batteries basically fall into 3 categories based on reversibility. Primary cells are your standard single-use batteries. Once the chemistry is done, they're dead. Secondary cells feature reversible reactions, so you can plug them into a wall to push the electrons backward and recharge them. And then we have fuel cells, which operate continuously as long as you keep feeding them fuel.
Take the everyday alkaline battery, the ones you pop into your TV remote. That is a classic primary cell. Developed back in the 50s, it actually replaced older zinc-carbon dry cells because it delivered way more energy. It uses a zinc powder anode and a manganese dioxide cathode. But a quick warning, because it's a primary cell, trying to recharge it is a terrible idea. It can violently rupture and leak out highly toxic caustic potassium hydroxide, so yeah, don't do that.
On the flip side, we have the lithium-ion battery. This is a secondary cell. And let's be real, it's the undisputed king of modern portable electronics. See how the lithium ions actually physically shuttle back and forth between the electrodes when charging and discharging? They're everywhere because they are incredibly lightweight, provide a massive amount of current with a steady voltage, and can handle hundreds of recharge cycles like an absolute champ.
Now compare your phone battery to your car battery. The workhorse of the automotive industry is the lead-acid battery. It's heavy, it's caustic, and it essentially strings 6 2-volt secondary cells together to get 12 volts total. Sure, they weigh a ton compared to lithium-ion, but they are still the absolute standard for cars because they can reliably dump that massive, sudden surge of current you need to crank a heavy starter motor.
Finally, let's look at fuel cells. These perform the exact same fundamental redox chemistry we've been covering, but they are a totally different beast. Instead of storing all their chemical reactants inside a closed box, they continuously draw in combustive fuels, like hydrogen gas or methane, along with an oxidant. By using platinum-based catalysts, they pull off this highly efficient electrochemical energy conversion that absolutely crushes traditional combustion in terms of efficiency. I want to leave you with this thought. We've gone from tracking a single invisible electron all the way to starting heavy machinery. But if we can truly master fuel cells, which are basically infinite electrochemical flow batteries that never die as long as fuel keeps pumping in, just imagine how completely that could transform our portable devices, our vehicles, and the very foundation of the energy grid we rely on every single day.